In this chapter, we'll look at prompt engineering as the first tool for adapting a model. We'll start with what it is, why it matters, and how to use it well before moving on to more advanced methods. Prompt engineering means designing the instruction so the model produces the outcome you need. It changes behavior through the prompt, not by retraining the model, which makes it the simplest and most common adaptation approach. It can look like trial and error, but effective prompting is more than word choice. Think of it as communication. Anyone can speak to a model, but getting a reliable result takes clarity, structure, and intention. Prompt engineering should still be handled scientifically. That means testing changes systematically, comparing results, and evaluating them carefully instead of relying on intuition alone. Prompting is a real skill, but production systems need more than that. You also need engineering, statistics, and machine learning practice for tracking experiments, evaluating quality, and curating data. This chapter covers both sides: how to write better prompts and how to protect applications from prompt attacks. We'll begin with the basics, then build toward practical prompting patterns and best practices. In this section, we define what a prompt is and break it into the parts that make it effective. You'll also see why model quality and prompt structure both matter. At the simplest level, prompting means giving the model a task to do. That task might be a direct question, or it might be a much larger workflow like research, coding, or data analysis. Most prompts are built from a small set of ingredients. The first one is the task itself, and the next one is often examples that show the model what good work looks like. The task description tells the model what job it should do. Is the core instruction around which the rest of the prompt is organized. This is where you specify the role, the expected behavior, and the shape of the answer. Being explicit here helps the model produce something that is easier to use. Examples show the model the pattern you want. They are especially useful when the task has subtle categories or a specific style of response. If you want to detect toxicity, examples of toxic and non-toxic text make the boundary much clearer. That usually improves consistency more than vague instructions alone. This is the concrete thing you want done. It might be a question to answer, a document to summarize, or a structure to fill in. The more specific the task, the easier it is for the model to respond correctly. Ambiguity here usually leads to ambiguity in the output. Here we have a very simple prompt for named entity recognition. The point is to show that even a short prompt can work if the task is clearly stated. Notice how compact the prompt is in the figure. It is a good reminder that a prompt does not need to be long to be useful. It needs to be clear. This figure is just a concrete example of the idea we've been discussing. It shows how a task statement alone can guide the model toward a specific extraction job. Prompting only works if the model can actually follow instructions. If that ability is weak, even a well-written prompt will not save the result. Some models are sensitive to tiny wording changes, like numerals, line breaks, or capitalization. That sensitivity tells you how much prompt tuning you may need. A robust model gives similar answers even when the prompt changes slightly. That is one reason stronger models often save time. You spend less effort fine-tuning the exact wording. Now we move from theory to practice. The main lesson is to test prompt structure yourself, because different models may prefer different layouts. Try moving the task description around and see what changes. Many models do well when the task is near the start, but some behave better when it appears at the end, so empirical testing matters. In this section, we'll look at how prompts can teach a model at inference time without changing its weights. We'll define zero-shot and few-shot learning, and then look at why the idea matters in practice. This is called in-context learning. The model picks up the task from examples or instructions in the prompt. The key idea is that the weights stay fixed, yet the model can still adapt to new tasks like translation, math, or question answering from context alone. That makes prompts a way to keep a model useful after its training data gets stale. If the model's knowledge is out of date, you can place the latest information directly in context and let it answer from that instead of retraining it. The vocabulary is simple. Each example in the prompt is a shot. So a prompt with a few examples is few-shot learning. 5 examples is 5-shot. And if you give no examples at all, that is zero-shot learning. There is no universal best number of examples. You usually have to test what works for your task, because more examples can improve behavior but also consume more context and increase inference cost. Earlier models like GPT-3 often improve a lot with few-shot prompts, but stronger models can already follow instructions well, so the gap is smaller. Even so, examples still matter when your task is specialized and the model has seen little of that domain during training. In this section, we'll sort out a common terminology problem. Different sources use prompt and context in different ways, so the important thing is to notice the definition being used. In the GPT-3 paper, context refers to the entire input given to the model, which makes it effectively the same as the prompt. So in that usage, the two words point to the same thing. Other people use context more narrowly to mean the information that helps the model do the task. In that sense, the prompt asks for something, and the context supplies the facts or background it needs. Google's Palm 2 documentation uses context even more broadly. It includes instructions about style, topics, and allowed wording. That makes context very close to the task description itself. To avoid confusion, this book uses a consistent convention. The prompt is the whole input, and the context is the part that helps the model carry out the task. Today, in-context learning is normal, but earlier models could only do what they were trained to do. That is why GPT-3 felt surprising. Prompt engineering suddenly looked like finding the right trigger for a capability already latent in the model. In this section, we'll separate two parts of a model input, the system prompt and the user prompt. This distinction matters because it helps you control the model's role and the specific request it should answer. A useful way to think about it is this. The system prompt sets the instructions, and the user prompt contains the actual task. Let's use a concrete example so you can see how developers use that split in practice. Suppose you're building a chatbot for property disclosures. The role, like acting as a real estate agent, belongs in the system prompt, while the buyer's question and the disclosure content go in the user prompt. That separation keeps the app's behavior consistent across many different questions. Here the system prompt defines the agent persona and the style of the answer. The user prompt supplies the specific document and asks a focused question, so the model knows both how to behave and what to solve. Notice how the instructions and the data are separated cleanly. In practice, most generative AI apps use a system prompt for developer instructions and a user prompt for the end user's request. You can experiment with different arrangements, but the point is to understand how the final behavior changes when instructions move between those parts. A model usually does not receive these pieces separately. Instead, the system prompt and user prompt are merged into one final input using a chat template defined by the model provider. Here we're looking at the template used by Llama 2. This template shows exactly where the system message and user message go. The placeholders get filled in before the prompt is sent to the model, so the formatting has to match the model's expected structure precisely. To make that concrete, imagine the system prompt says to translate into French and the user asks a simple question. The next block shows the fully assembled prompt exactly as Llama 2 expects to receive it. This is the final combined prompt. The instruction comes first inside the system section, and the user message follows after it, all wrapped in the model's required tokens. Now let's pause for an important distinction. A model's chat template is not the same thing as an application-level prompt template, and mixing those up is a common source of errors. The chat template is part of the model's own expected input format, and it is usually documented by the model provider. A prompt template, by contrast, is something an application developer uses to fill in variables before sending a request. Different model families can use different chat templates, and even the same provider may change them across versions. So you should not assume one formatting scheme works everywhere. Always check the documentation for the exact model you are using. This Llama 3 template uses a different set of special tokens and headers, but the idea is the same. The system prompt, user prompt, and assistant turn are all laid out in a specific order that the model has been trained to recognize. A token like beginning of occur text is not multiple characters to the model. It is treated as one token. That matters because these markers are part of the model's learned structure, not just decorative text. Even tiny formatting errors, such as using the wrong template or adding an extra new line, can cause strange performance problems. The model may still answer something reasonable, which makes these bugs hard to notice. Here are a few practical habits that help avoid template bugs. These are simple checks, but they save a lot of debugging time when you work with foundation models. The main idea is to be strict about formatting and to verify what actually gets sent to the model. The next few lines give you 3 concrete habits that reduce mismatched template problems. First, keep the model's expected structure in mind. When you build a request, follow the model's chat template exactly. Even small deviations can change how the model interprets the prompt. Second, verify any tool you rely on. If a library or service assembles the prompt for you, confirm that it uses the correct template. These mistakes are common, and they can fail silently because the model still produces an answer even when the formatting is off. Third, inspect the final prompt before sending it. A quick printout of the assembled prompt is one of the easiest ways to catch formatting issues. If the final string looks right, you're much less likely to ship a hidden template bug. Many providers say that a carefully written system prompt can improve performance, especially when you want the model to stay in a role or follow a consistent style. The prompt gives the model a strong, persistent framing for the conversation. Under the hood, both prompts are merged into one final input, so the model sees a single sequence of text. Any benefit from the system prompt likely comes from where it appears in that sequence, or from extra training that teaches the model to pay special attention to it. There are 2 likely explanations for the effect. Let's look at them one by one. One possibility is simple ordering. The system prompt appears first, and models may handle early instructions more effectively. That would make the placement itself part of the performance advantage. The second explanation is training and prioritization. Another possibility is that the model has been post-trained to treat system instructions as higher priority. That also helps defend against prompt attacks, because the model learns to follow the privileged instructions more reliably. Now we're looking at a practical limit on prompts. How much text a model can actually hold at once. Then we'll see why simply making context longer is not enough. You also have to use that context efficiently. A model can only read as much text as fits inside its context window. Early GPT models had very small windows by today's standards, which meant they could not comfortably handle long essays, legal contracts, or research papers. Context length has expanded dramatically in just a few years. That jump matters because it changes what kinds of tasks become feasible, from short prompts to book-length documents and even sizable code bases. This chart shows the scale of that change. The important thing to notice is how quickly the limit moved from a few thousand tokens to millions, which completely changes how we can design prompts and applications. This figure gives the timeline behind the trend. It's a reminder that context length is not fixed. It is a moving target, and newer models can often handle much more than earlier ones. Long prompts are not treated uniformly. Research shows that models tend to pay more attention to information near the start and the end, so placement inside the prompt can affect performance. This example demonstrates the test. Hide one important fact inside a long block of text and ask the model to recover it. The key idea is to measure whether the model can find the hidden information no matter where it appears. This figure shows what the test looks like in practice. The point is not the exact content of the prompt, but the structure, one target item placed inside a much larger context. The result is clear. Models generally retrieve the inserted information more reliably when it appears near the beginning or the end. That is why prompt structure matters, not just prompt length. This graph shows the pattern visually. When the relevant information sits in the middle of a long prompt, performance tends to fall, which is a useful warning when you're building long context applications. Here the message is even more explicit. Where you place information changes how well the model can use it. Lower positions on the figure are closer to the start of the input context. You do not need random strings to run this kind of test. Real transcripts or documents can work too, as long as the information is private, so the model cannot answer from memory instead of the prompt itself. Other benchmarks, like Ruler, test long context processing in a more systematic way. If accuracy gets worse as prompts get longer, that is a sign you should reduce prompt size or reorganize the information. At this point, the main pieces of a prompt should be clear: system prompt, user prompt, examples, and context. Next, we move from understanding prompts to writing them well with practical best practices. Now we'll shift from clever prompt hacks to techniques that hold up across models. The goal here is to focus on methods that are practical, durable, and worth remembering. Early prompt engineering often relied on brittle tricks, like changing wording or adding artificial incentives to coax better answers from weaker models. Those techniques can work, but they often stop helping as models become better at following instructions and handling variation. In this section, we'll concentrate on practices that have been tested across a wide range of models and are likely to stay useful. These recommendations are drawn from major model providers and from teams that have already shipped real generative AI products. Even with general best practices, every model has its own quirks. So when you work with a specific model, look for its own prompt guide or examples, because small details can make a big difference. In this section, we focus on a simple rule: the clearer your prompt, the more reliable the model's response. You'll see 3 practical ways to remove ambiguity and guide the output you want. Think of prompting as giving instructions to a person. If the request is vague, the result is unpredictable. The goal here is to make your instructions specific enough that the model has less room to guess. First, describe the task with no ambiguity. If you want a score, a label, or a decision, say so directly and define the rules the model should follow. If the model is scoring an essay, you need to specify the scale and what to do when the answer is uncertain. That way, the model is not forced to invent its own scoring system or its own fallback behavior. Prompting is often an iterative process. If you notice outputs like fractional scores and you only want whole numbers, tighten the instruction so the model knows exactly which format is allowed. A persona gives the model a point of view that can change how it interprets the task and helps it respond in a style that matches your use case. The same essay can receive different scores depending on the perspective you ask for. A first-grade teacher, for example, will judge the writing differently than a generic model prompt because the evaluation criteria shift with the role. This image illustrates the idea of prompting with a role or context. The important point is not the exact picture, but the reminder that the model's answer changes when you tell it what perspective to use. This figure reinforces the same lesson. Giving the model a role can make its response better aligned with your goal. It is a simple way to steer the model toward the right kind of answer. Another strong technique is to show the model examples of the behavior you want. Examples reduce guesswork and make the desired pattern much easier to imitate. If you're building a bot for children, a literal factual answer may be the wrong tone. An example shows the model how to respond in a way that fits the audience and the application. By including examples, you can nudge the model toward the kind of answer you want, even for tricky topics like fictional characters. The example teaches the format and the style at the same time. Here the table shows the difference clearly. Without an example, the response may drift into an unwanted explanation, but with a sample Q&A pattern, the model follows the style you demonstrated. The key lesson is that few-shot examples can steer both content and tone. Examples are helpful, but they also consume tokens. If two prompt formats work equally well, choose the shorter one so you save cost and reduce latency. This table compares two equivalent prompt styles and shows that one uses fewer tokens. In practice, that matters because token count affects both price and speed, so brevity is worth optimizing when performance is the same. Once the task itself is clear, define the shape of the response. That makes the result easier to parse, easier to use, and less likely to include extra text you do not want. If you want a short response, say that explicitly. This reduces unnecessary tokens, lowers latency, and helps keep the answer focused on the final result instead of a preamble. When another system will consume the model's output, the format must be precise. If you want JSON, name the keys you expect and show an example when needed, so the model has a concrete template to follow. For classification and similar tasks, a clear marker tells the model when the input ends and the answer should begin. Choosing a marker that does not appear in the input helps prevent the model from confusing the prompt with the output format. This table shows the failure mode and the fix. Without a boundary marker, the model keeps extending the pattern from the input. With a marker like an arrow at the end, it knows to produce just the label. In this section, we'll look at why context matters so much for model performance. The basic idea is simple. Better context usually leads to better answers. Think of context like the reference material a student brings into an exam. If the model has the paper, the facts, or the relevant background, it can answer more accurately and with fewer mistakes. Without that information, it may guess from its own internal knowledge, and that is where hallucinations often begin. So there are two main approaches. Give the model the needed information directly, or let it fetch that information first. That retrieval step is called context construction, and it includes tools like RAG and web search. We'll come back to those tools later in Chapter 6. In this section, we'll look at how to make a model answer using only the information you give it. This matters most in simulations, role play, and retrieval-style tasks where outside knowledge would break the illusion or the constraint. The goal is to keep the model inside a narrow world of facts. For example, a Skyrim character should speak like it lives in that universe, not suddenly answer with outside world knowledge like a Starbucks order. A strong prompt can improve compliance. Tell the model to answer only from the context and show examples of questions it should refuse. Asking it to quote the source can also encourage grounded answers, because it has to point to evidence instead of inventing one. But prompting is still just guidance, not a guarantee. Fine-tuning on your corpus helps, but pre-training knowledge can still leak through. The most reliable approach is training only on the approved data, though that is often expensive and the dataset may be too small to produce a strong model. When a task has several steps, it often works better to split it into smaller prompts. In this section, we'll see how decomposition improves reliability, makes debugging easier, and can even reduce cost. The core idea is simple. Don't ask one prompt to do everything at once. break the work into focused subtasks, then chain the outputs together so each step has a clear responsibility. A good example is customer support, where the first step is often to identify what kind of request the user is making. This step classifies the user's message into an intent. Once you know the intent, the rest of the system can choose the right behavior. After that, the system can move to the second step, generating the actual response for that intent. Now the prompt can be specialized. If there are many possible intents, you may end up with many small response prompts, but each one is simpler and more controlled. This example shows the pattern in practice. One prompt classifies the request, and another prompt handles a specific intent, such as troubleshooting. That separation keeps each prompt narrow and easier to manage. Here you can see the decomposition directly. The first prompt forces a structured classification output, while the second prompt uses that classification to drive troubleshooting behavior. Notice how the second prompt can focus on one case instead of handling every possibility. There's no single perfect cut. The right level of decomposition depends on the task, along with the cost, latency, and quality trade-offs you're willing to make. Even though models are improving, they still tend to handle simpler instructions more reliably. That's why decomposition often improves both performance and control. One major benefit is visibility. When a workflow is split into steps, you can inspect each stage instead of only seeing the final answer. That makes it much easier to understand where the process is going right or wrong. You're not debugging a black box anymore. You're watching the pipeline step by step. Decomposition also helps when something fails. You can focus on a specific step that is causing trouble instead of rewriting the whole prompt. That isolation is valuable because it lets you improve one part of the system while leaving the other part stable. It's a much safer way to iterate. Another benefit appears when steps are independent. If they do not depend on each other, you can run them in parallel and save time. For example, three versions of the same story for different reading levels can be generated simultaneously. That reduces total latency because the work happens at once instead of one version after another. Decomposition also lowers the writing burden. It is often much easier to author several simple prompts than one very complicated prompt. That matters in real projects, because prompt design becomes more manageable when each prompt has a narrow job and fewer edge cases. The downside is that extra steps can increase the time before users see a result. If the intermediate outputs are hidden, the workflow may feel slower even when each step is small. More prompts usually mean more API calls, so cost can rise. But the increase is not always linear, because smaller prompts use fewer tokens, and you can often use cheaper models for simpler steps. In practice, prompts can grow very large as you add instructions and examples. Breaking them apart can improve performance and reduce token usage at the same time, which is why decomposition is often worth testing. Sometimes better answers come from giving the model more room to work through the problem. In this section, we'll look at prompting patterns that encourage deeper reasoning and also the trade-off. More thinking can mean more latency. One practical way to improve responses is to ask the model to reason more carefully, using chain-of-thought prompting or self-critique. The goal is to nudge the model toward a more deliberate process instead of a quick guess. Chain of thought asks the model to work through the problem step by step, which often improves consistency on reasoning tasks. It's an old but important technique, and it has been shown to help across different models and benchmarks, including reducing hallucinations in some settings. This figure is showing that the benefit of COT is not limited to one model or one benchmark. Notice the improvement across multiple model families and mass-style tasks. That's the key takeaway. The caption reinforces the main point. Asking for explicit reasoning can help models like Lambda, GPT-3, and PaLM perform better on word problem benchmarks. It's a good reminder that prompt structure can change output quality in measurable ways. The simplest version is just to ask for a step-by-step answer or for the model to explain its decision. If you want more control, you can spell out the steps yourself or show an example of the reasoning format you want. These examples show the same question written in different ways, from a simple step-by-step instruction to a one-shot example. What matters is that the best variation depends on the task, so you often need to test a few formats to see which one performs best. Self-critique asks the model to review what it just produced and evaluate whether it makes sense. Like chain of thought, it encourages a more careful response, but now the focus is on checking and refining rather than only generating. There's a cost to this approach. If the model does extra internal work before showing the first token, users wait longer. And if the steps are generated automatically, the delay and compute cost can grow quickly. Prompt writing gets better through revision. In this section, we'll look at how to test your prompts, notice what the model is doing, and adjust your wording to get better results. A good prompt is rarely perfect on the first try. If the model responds too cautiously, too broadly, or not in the way you intended, use that result to refine your wording and make the request more specific. Different models have different strengths, and they may also react differently to the same instruction order. The best way to learn is to experiment. Try multiple prompts, compare models, read the developer's guidance, and use a playground if one is available. When you change a prompt, track that change carefully so you know what actually improved. Version your prompts. Use consistent evaluation data and metrics, and judge the prompt in the context of the whole system, not just one isolated task. In this section, we look at tools that help automate prompt engineering. The key question is not just whether they work, but how they work and what trade-offs they introduce. For any task, there are countless possible prompts, so testing them by hand quickly becomes slow and impractical. That is why people build tools to search for better prompts automatically. Some systems try to automate the whole workflow. You define the input and output structure, the metric, and the evaluation set. Then the tool searches for a prompt or prompt chain that scores well, much like AutoML searches for strong model settings. Another approach is to use the model itself as the prompt writing assistant. You can ask it to generate a prompt, improve an existing one, or create in-context examples to make the task clearer. Prompt Breeder and TextGrad are examples of AI-powered prompt optimization. Prompt Breeder works like evolution. It starts with one prompt, mutates it, keeps the best variants, and repeats until it finds a stronger prompt. Here, the important thing is that a language model is being used to produce a prompt, not just an answer. This shows how AI can assist the prompt design step itself. This figure illustrates the simplest version of prompt automation. The model is not solving the final task yet. It is helping you draft the instruction that will later be used for the task. This diagram shows the loop clearly. Start with a prompt, generate mutations, evaluate them, and keep the most promising ones. The main idea is repeated improvement through selection. Prompt Breeder treats prompts like candidates in an optimization process. The best ones are mutated again, which makes the search more systematic than ad hoc trial and error. Not every tool tries to solve the entire problem. Some focus on structured outputs, while others test prompt variations to see which version performs best. Used well, these tools can improve results a lot. But the real advantage comes when you understand what the tool is doing behind the scenes instead of treating it like a black box. The first risk is cost. A tool may generate many prompt variations and evaluate each one, which can turn a small experiment into hundreds of API calls very quickly. A single prompt can trigger multiple model calls, one to generate, one to validate, and one to score. If the tool is allowed to build long prompt chains, the cost and latency can grow even more. The second risk is correctness. Tool authors can use the wrong template, build prompts incorrectly, or even ship typos in the default prompt text, and those mistakes can affect your results. This image is a reminder that even default prompts can contain small errors. The lesson is to inspect tool-generated text carefully instead of assuming it is always correct. This figure highlights a practical warning. Even widely used tools can have mistakes in their built-in prompts. Small wording errors may seem minor, but they can change how the model behaves. There is also maintenance risk. Tools can change their templates or defaults over time, and the more tools you stack together, the harder it becomes to trace where an error came from. A good rule is to begin without tools. Writing your own prompts first helps you understand the model's behavior and clarifies what your application actually needs. If you do use a tool, check the prompts it produces and count the API calls it generates. The point is to keep control of both quality and cost, because tool authors can still make mistakes. Now we'll look at how to keep prompts maintainable as your project grows. The key idea is to treat prompts like a first-class asset, not just inline text buried in application code. A good starting point is to store prompts separately from the application logic. That makes it easier to update, reuse, and inspect prompts without mixing them into the rest of the program. This pattern keeps the prompt in one place and imports it wherever the application needs it. Notice that the prompt is passed as the system message, while the user input stays separate, which makes the query structure much clearer. Once the prompt is isolated, the rest of the benefits become easier to see. We can optimize prompts without digging through application logic every time. The same prompt can be shared across multiple applications. That reduces duplication and keeps behavior more consistent. Instead of copying prompt text into several code bases, you keep a single source of truth. When the prompt improves, every caller can benefit from it. Separating prompts from code also makes evaluation much easier. You can test the application logic independently, and then compare how different prompts change the model's response. This is especially useful when you want to run the same code against several prompt versions. It helps you tell whether a bug comes from the application or from the prompt itself. There's also a simple readability benefit. Short, focused files are easier for engineers to understand at a glance. When prompts are separated out, each piece becomes easier to scan and review. That lowers the chance of accidental changes and makes maintenance simpler. This structure also helps teams work together. Prompt writers and subject matter experts can focus on the language, while engineers focus on the integration. That separation matters because prompt quality often improves when non-engineers can review it without needing to understand the whole code base. It makes collaboration much smoother. If you manage many prompts, you should attach metadata so they can be tracked and searched. Information like the application, model, and creator helps you know exactly what each prompt is for. Here the prompt is wrapped in a structured object. That lets you store not just the text, but also useful fields like when it was created, which application uses it, and who wrote it. A prompt template can carry more than the instructions themselves. It can also describe how the prompt should be deployed and what it expects on input and output. These bullets are examples of the extra fields that make a prompt easier to manage in a larger system. Storing the endpoint helps the system know where the prompt is meant to run. That matters when different prompts are tied to different model deployments. Next comes the model configuration itself, which is often just as important as the prompt text. Parameters like temperature and top P affect how the model responds. Saving them with the prompt helps you reproduce the same behavior later. The input definition is another part of the contract between the prompt and the application. A schema makes it clear what data the prompt expects. That reduces ambiguity and makes integration safer. And finally, you can record what the model should return so downstream code knows how to handle it. This is especially important for structured outputs. If you know the shape of the response ahead of time, you can validate it and consume it more reliably. Some tools define dedicated file formats for storing prompts and their metadata. The goal is the same: make prompts easier to manage, search, and reuse across a team. This .prompt example combines configuration and prompt text in one file. Notice how the header declares the model, the input schema, and the expected JSON output, so the prompt is self-describing. If prompts live in the same repository as the code, Git can version them automatically. But that also means a shared prompt change can force every application onto the newest version, which is not always what a team wants. That is why many teams adopt a separate prompt catalog. It lets each application choose a specific prompt version, while still keeping metadata, search, and dependency tracking in one place. In this section, we shift from building prompts to defending them. The goal is to understand the main attack patterns and why they matter for real applications. Once an application is public, it has two audiences: the people you designed it for and people trying to break it. So we need to think in terms of attack surfaces, not just helpful behavior. The first attack is prompt extraction. Here the attacker is trying to uncover the hidden instructions that shape the model's behavior. If an attacker can recover your system prompt, they may be able to copy your app's behavior or find ways around its safeguards. That hidden prompt is often part of the security boundary. The second class is jailbreaking and prompt injection. In both cases, the attacker tries to override the model's normal instructions and steer it into unsafe behavior. The outcome here is simple. The model is pushed to ignore rules or safety boundaries. That can turn a helpful system into one that behaves dangerously or unreliably. The third attack is information extraction. Instead of changing behavior, the attacker tries to reveal private or sensitive information from the model's context or training data. This matters because the model may have access to data it should not disclose. If that information leaks, the impact can extend beyond the application itself to users and internal systems. These attacks are not just theoretical. They can lead to very different kinds of damage, from security failures to public trust problems. One major risk is unauthorized tool use or code execution. If an attacker can control a tool-bearing model, they may be able to trigger actions that go far beyond conversation. With access to tools, an attacker might make the system run harmful SQL, send unauthorized emails, or generate malicious code. The danger is not just bad text. It is real actions in the outside world. Another risk is exposure of private data. A model that reveals user, system, or internal information can create serious confidentiality problems. The issue here is straightforward. If the attacker gets sensitive details, they may be able to misuse them immediately. Even a small leak can have broad consequences. Prompt attacks can also be used to amplify harmful content. In that case, the model becomes a tool for dangerous or criminal guidance instead of safe assistance. This can include instructions for weapons, tax evasion, or stealing personal information. The model is not just making a mistake. It is helping an attacker cause real harm. A different failure mode is misinformation. Here, the attacker wants the model to say something false in a way that supports an agenda. This is especially dangerous because the output can look confident and authoritative. If users trust it, the misinformation spreads quickly. Attackers can also disrupt service or manipulate decisions. In these cases, the model is used to break workflows rather than to leak data. That might mean giving access to someone who should not have it, inflating scores, rejecting good applications, or forcing the model to refuse everything. The harm is operational, and sometimes it is directly business critical. Finally, there is brand risk. Even when the content is produced by an attacker, users still associate the output with your product. A toxic or politically incorrect response next to your logo can trigger a public relations crisis. The examples show how quickly people can blame the product owner for unsafe behavior. As models get more capable, the consequences of prompt attacks grow too. Next, we will look at how these attacks happen in practice and how to defend against them. In this section, we'll look at why prompts can become valuable assets and why that makes them a target. We'll also see how reverse prompt engineering works and why secrecy alone is rarely a strong defense. Because good prompts take real time to develop, people often treat them like reusable assets. That has led to public repositories, marketplaces, and internal sharing systems where teams trade and reuse prompts that work well. But not every organization wants to share. Many teams see prompts as proprietary know-how, and there is even debate about whether a prompt can be patented. That tension is part of why prompts are now treated like intellectual property. The more hidden a prompt is, the more tempting it becomes to reconstruct it. Reverse prompt engineering means trying to infer the system prompt behind an application, either to copy the behavior or to exploit it. People usually do this by studying responses or by prompting the model to repeat its own instructions. The warning here is simple. Assume anything embedded in a prompt may eventually be exposed, so don't rely on secrecy alone. This example shows a simple prompt injection style attack. The first lines establish a pattern. Then the model is told to ignore prior text and follow a new instruction. The goal is to get it to reveal or override its hidden guidance. Popular systems like ChatGPT are frequent targets, but a leaked-looking prompt is not automatically real. The hard part is verification, and in many cases the model is just generating something plausible rather than exposing its true internal instructions. This is not only about system prompts. If sensitive information is placed in the model's context, a user may be able to coax it back out, which is why context should be treated as potentially exposed as well. Notice how the conversation exposes information that was supposed to stay hidden. The key lesson is that model responses can leak both instructions and user-specific data if the application is not carefully designed. This figure reinforces the risk with a concrete example. Even when the system is told not to reveal something, the model may still surface it if the surrounding setup is weak enough. The final takeaway is that prompts are rarely a durable moat. They need ongoing maintenance, and any model update can force you to rewrite them, so their value is often lower than teams first assume. In this section, we'll separate two closely related attack patterns and see why they matter for real AI systems. We'll also look at the main techniques attackers use and how those techniques show up in tools, retrieval, and chat workflows. Jailbreaking means trying to push a model past its safety boundaries. In practice, that could mean persuading a chatbot to give dangerous or forbidden instructions that it was meant to refuse. Prompt injection is different in form, but similar in goal. The attacker hides harmful instructions inside what looks like an ordinary prompt. If the model follows those hidden instructions instead of the real user intent, the attack succeeds. These terms are easy to mix up because both are about getting undesired behavior from a model. In this book, the word jailbreaking is used broadly to cover both cases, so you can focus on the attack pattern rather than the label. Before we go further, there's an important distinction. Some undesirable behavior is caused by an attacker, and some happens even when honest users interact with the model normally. This section is mainly about adversarial misuse, but models can still produce harmful outputs without any malicious intent from a user. That matters because safety has to handle both deliberate attacks and accidental failures. Even aligned models have been coaxed into giving weapon instructions, toxic replies, illegal drug advice, or extreme roleplay. The point is not that alignment fails completely, but that it does not automatically remove every harmful behavior. Prompt attacks work because instruction following is exactly what these models are trained to do. That creates a tension. The same ability that makes them useful also makes them easier to steer with malicious instructions, especially when system and user intent conflict. Like cybersecurity more broadly, this is an arms race. Defenses improve, attackers adapt, and older tricks tend to stop working once models and filters get better. We'll start with the simplest class of attacks, handwritten prompts. These are the kinds of attempts where a person manually experiments with wording until the model slips. This is basically social engineering for models. Instead of persuading a human, the attacker keeps rephrasing and nudging the model until it stops refusing and starts answering the wrong thing. A classic early trick was obfuscation, where attackers misspell or disguise blocked words so a keyword filter misses them. Models often still understand the meaning, which is why simple spelling filters are not enough. Attackers also tried adding odd characters or formatting noise to confuse the model or the filter. That can work against brittle defenses, but it is easy to block if the system checks for obviously suspicious character patterns. Another approach is to wrap the harmful request in a different style, like a poem or song. The model may focus on the format instead of the underlying intent, which is why output style alone is not a reliable safety boundary. Roleplay attacks try to lower the model's guard by asking it to act out a character or scenario. The old damn prompts are a well-known example. They try to convince the model that normal rules no longer apply. This prompt is trying to redefine the model's identity and constraints. Notice the key tactic. It asks the model to adopt a persona, then claims that persona has fewer rules than the real assistant, which is exactly the kind of pressure safety systems are designed to resist. Once attackers saw that roleplay could sometimes work, they kept inventing new characters and scenarios. The exact story changes, but the pattern is the same. Create a fictional frame that encourages the model to ignore its normal constraints. Manual prompting is only the first step. Next, we get to attacks that use algorithms or even another model to search for a jailbreak automatically. Instead of guessing by hand, attackers can generate many prompt variations and test them systematically. That makes the attack faster, more scalable, and often more effective than one-off prompting. Pair is a stronger version of this idea. Here, one model plays the attacker and iteratively refines prompts based on the target model's replies, so the attack improves from feedback instead of from manual trial and error. First, the attacker model generates a candidate prompt. This is the starting guess, an initial prompt designed to elicit the unwanted behavior from the target. Then the prompt is sent to the target model. Now, the target responds, and that response becomes the next source of information for the attacker. After that, the attacker updates the prompt and tries again. This loop continues until the attacker reaches the objective or runs out of budget. The important idea is that the attack gets better by using the model's own feedback against it. This diagram shows the attacker and target loop visually. Watch for the repeated cycle: propose, test, observe, and refine until the jailbreak succeeds. Pair is powerful because it automates the search process. In the paper's experiments, it often needs surprisingly few queries to find a successful jailbreak, which shows how efficient feedback-driven attacks can be. That low query count is the key takeaway. It means a targeted attack can succeed quickly once the attacker has a model that can systematically explore the space of prompts. Now we move to a more dangerous class of attacks. Instead of attacking the prompt you type directly, the attacker hides instructions in external content that the model later reads through tools. This is stronger because the attack can arrive through web pages, emails, files, or any other tool-connected source. The model may treat that content as data, even though it secretly contains instructions. Look at this as a tool-using system. The robot is not just answering questions, it is also reading outside content. That extra access is what makes indirect injection so risky. The danger here is that the model may retrieve hostile content and then act on it. Once retrieval and execution are connected, the attacker no longer has to speak to the model directly. Because modern agents can use many different tools, indirect attacks can take many forms. We'll look at two broad patterns: passive phishing and active injection. The first pattern is passive phishing. In passive phishing, the attacker plants malicious content in public places and waits for a model to discover it through search or retrieval. The content looks harmless to a person, but can become dangerous once an agent starts using it as evidence or code. A public repository, comment, or web page can hide instructions that later get pulled into an AI coding workflow. If the model recommends code from that source, a user may execute attacker-controlled behavior without realizing it. The second pattern is active injection. Active injection is more direct. The attacker sends the malicious content straight to the target, often through email or another user-facing channel. When the assistant reads that content, it can mistakenly treat the attacker's words as commands. This is a good example of why tool use is risky. An email assistant may read an attacker's message, confuse it with the user's intent, and then carry out an action the attacker wanted all along. This trace shows the failure mode clearly. The assistant reads a normal email, but the tool output contains a hidden instruction, and the model mistakenly follows it as if it were part of the task. The same pattern shows up in retrieval-augmented systems, where retrieved text can influence the model's next action. If the retrieved content contains deceptive wording, the model may interpret it as a command rather than as untrusted data. Traditional databases often rely on sanitization to block SQL injection, but natural language is much harder to sanitize cleanly. That is why prompt injection is so tricky. Malicious intent can hide inside text that looks perfectly ordinary. In this section, we look at how language models can leak what they know or what they were trained on. The key issue is that a model's knowledge can be accessed in ways that were never intended by the people who built it. A conversational model could be very powerful because it stores a large amount of information in a form people can query naturally. But that same interface can be abused to pull out data the model should not reveal. One risk is plain data theft. If an attacker can recover training data, they may be able to reuse expensive data collection work for their own competitive model. That matters because training data is often costly to gather and curate. If competitors can extract it, they save time and money while undermining the original model developer. The second major risk is privacy. A model may expose sensitive information from its training set or from private context it has been given. This can include personal emails, private messages, or other confidential records. If a model memorizes those details, extraction attacks can turn that memorization into a privacy breach. A third risk is copyright. If a model has learned copyrighted material, it may reproduce protected text or other content in response to the right prompt. In practice, that means the model can sometimes echo back copyrighted passages instead of generating something new. Even when it happens accidentally, it can create legal and business risk. Researchers also study a related idea called factual probing, which asks what a model knows rather than what it will reveal verbatim. Benchmarks like llama test relational facts with fill-in-the-blank prompts, such as who was born where, or what category something belongs to. The same prompting style can be turned against the model. If it memorized training examples, a carefully chosen prompt may cause it to complete the exact sensitive string the attacker wants. Earlier work showed that extraction can succeed, but often only when the attacker knows the surrounding context of the original text. A very specific prompt is more likely to recover the memorized data than a broad, generic one. Later work showed something more worrying. You may not need the exact training context at all. If the model is pushed into a long, repetitive loop and then starts diverging, some of the outputs can come directly from training data. This screenshot illustrates the idea. Notice the repetitive prompt behavior first, and then the shift into unusual output, which is where copied training text can start to appear. This figure shows the transition from harmless-looking repetition to a state where the model can begin divulging memorized text. It is a good example of how a prompt can look innocent while still producing a privacy leak. The study also found that larger models tend to memorize more, which makes them more vulnerable to extraction. That does not mean every memorized string is easy to recover, but it does mean scale can increase risk. This is not only a language model problem. Diffusion models can also reproduce training images so closely that the generated result is nearly identical to a real image, including logos and other copyrighted material. Here, the key thing to notice is the closeness between the generated output and a real-world image. That similarity is what makes training data extraction in image models such a serious privacy issue. This figure reinforces the point that model outputs can be more than inspired by training data. They can be extremely close copies. That is why privacy-preserving training matters even for image models. It is also important not to overstate the risk. Sometimes extracted text is ordinary material, not personal information, but the same techniques can still be dangerous when sensitive data is involved. One mitigation is to block suspicious fill-in-the-blank requests and filter outputs that contain personal data. That can reduce risk, though it will not eliminate it completely. Even without an adversarial attack, a model can sometimes regurgitate training material. If that material is copyrighted, the people using the system may inherit the legal consequences. Researchers have measured this by prompting models to continue copyrighted text and checking whether they reproduce it exactly. The result was that exact long-form copying is uncommon, but it does show up more with popular books. This screenshot shows a model being cautious about a fill-in-the-blank request. It is a reminder that safety filters can sometimes be overbroad and confuse benign completion with harmful copying. Here the model initially refuses, then changes course after the user corrects it. That tells us safety systems can be imperfect and sometimes need careful prompting or better policy design. The important nuance is that regurgitation does not have to be verbatim to create risk. Even transformed or disguised versions of copyrighted work can still lead to infringement concerns. That is why detection is so difficult. Legal judgment is often required, and automation is limited. The safest approach is to avoid training on copyrighted material in the first place, especially when you do not fully control the model. In this section, we'll look at how to defend an LLM-based system against prompt attacks. The key idea is to combine evaluation, model training, prompt design, and system controls rather than relying on just one fix. Before you can defend a system, you need to know what kinds of attacks it is vulnerable to. Benchmarks and probing tools help you test the model with known adversarial prompts, so you can see where it fails. A good security process also includes human red teaming. People try to break the system on purpose, which helps reveal weaknesses that automated tests may miss and leads to stronger defenses. Defenses can be added at several layers, inside the model, in the prompt, and in the surrounding system. Even so, if the system can do something impactful, prompt attacks may never be eliminated completely. Two metrics matter here. Violation rate tells you how often attacks succeed, while false refusal rate tells you how often the model refuses a request it could have answered safely. You want a system that is secure without becoming useless. Let's start with defenses built into the model itself. The goal is to teach the model which instructions deserve priority, so it can resist malicious instructions that appear in the prompt. Many attacks work because the model sees system instructions and attacker instructions as one mixed block of text. If the model is trained to recognize instruction hierarchy, it can follow the trusted instructions instead of the malicious ones. OpenAI's instruction hierarchy work is a concrete example of this idea. The model is trained to treat different instruction sources with different priority levels, which gives it a clear decision rule when instructions conflict. The first level in the hierarchy is the most trusted instruction source. This kind of layered structure helps the model decide what to obey when there's a conflict. At the top is the system prompt, which sets the core behavior and rules for the assistant. This instruction should usually win over anything the user or a tool says. Next comes the user-facing instruction level. It matters, but it should still be subordinate to the system policy when the two disagree. This is the user's request. The model should try to help, but not if the request conflicts with higher priority safety instructions. Lower priority sources come after the user prompt. This ordering is what makes the hierarchy useful for safety. The model's own output is also part of the hierarchy. Its response should reflect the higher priority instructions it has received, not arbitrary later text. And finally, there are tool-related messages, which should be treated carefully. They often carry useful data, but they are not the source of policy. Tool outputs are the lowest priority source here. That matters because a tool response might contain injected instructions, and a model should not obey them over trusted policy. This figure shows the hierarchy visually. Notice the clear ordering. System instructions are treated as more privileged than user text, model behavior, and tool output, which helps block indirect prompt injection. This caption names the core idea shown in the figure. The main point is not the exact wording, but the ordering of instruction sources by trust and priority. When instructions conflict, the higher priority one should be followed. That is what makes this approach effective against prompt injection coming through lower trust channels like tools. The paper reports that fine-tuning with this hierarchy improved safety evaluations while only slightly affecting normal capability. So the model becomes more resistant without losing most of its usefulness. Safety training should handle ambiguous cases, not just obviously malicious ones. The best system can refuse truly dangerous requests, but still offer safe alternatives when a request might have a legitimate purpose. Now let's move one layer up to the prompt itself. Here the goal is to write prompts that are harder for attackers to manipulate and easier for the model to follow correctly. A prompt can be made more robust by being explicit about what must never be returned. Clear constraints reduce ambiguity and leave less room for the model to follow a malicious interpretation. One simple strategy is to repeat the core instruction before and after the user content. The repetition acts like reinforcement, reminding the model what its job is even if the middle content is noisy or adversarial. This prompt shows the basic pattern. The task is stated, the paper text is inserted, and then the instruction is repeated so the model is more likely to stay on task. The benefit is better instruction persistence. The trade-off is that you spend more tokens and add latency because the prompt is now longer and the model has more text to process. If you already know common attack styles, you can mention them directly in the prompt. That helps the model recognize manipulation attempts instead of treating them as part of the task. This version is more defensive because it names likely jailbreak patterns. By anticipating those tricks in the prompt itself, you make it harder for the model to be redirected. If you use a prompt library or tool, inspect its default templates carefully. Some templates are too permissive, so adding explicit restrictions can make a big difference, although the model still may not always comply. The last layer is the surrounding system. Even if the model is imperfect, good system design can contain damage, block unsafe actions, and reduce what an attack can actually do. A simple and important rule is isolation. If generated code needs to run it in a sandbox or virtual machine, so any harmful behavior stays contained instead of reaching the user's real environment. For high-impact operations, add a human approval step. That way, sensitive commands like database modifications cannot happen automatically without review. You can also narrow the application's domain. If the system is built for customer support, it should not answer unrelated controversial questions, and simple input filtering can help enforce that boundary. More advanced systems look at the whole conversation, not just one message. That lets them spot suspicious intent or unusual behavior patterns and route risky requests to a human operator. Guardrails should exist on both sides. Detect suspicious inputs before they reach the model, and inspect outputs for PII, toxicity, or other harmful content. In practice, you need both layers because harmless-looking input can still produce a dangerous response. Finally, don't look only at single prompts. Repeated similar requests over a short period can signal someone probing your defenses, so usage patterns themselves are an important security signal. Let's wrap up the chapter by pulling together the main ideas. We'll review what prompt engineering is, why it matters, and where the risks and limitations come in. Foundation models are powerful, but they still need to be told exactly what to do. Prompt engineering is the work of shaping that instruction, and the amount of care needed depends on how sensitive the model is to changes in wording. A useful way to think about it is as communication between a person and a model. It looks easy at first, but getting consistently good results takes real skill, just like writing or speaking well to another person. The chapter then moves into practical guidance, how prompts are built, why examples help models learn in context, and what good prompting practices look like. Small changes like asking for step-by-step reasoning can make a big difference, but you also have to account for a model's quirks and biases. Because models follow instructions, they can also be manipulated with malicious ones. That's why the chapter covers prompt attacks and defenses, while emphasizing that security is never perfect and remains a serious concern in high-stakes settings. One important lesson is that instructions alone are not always sufficient. To complete a task well, a model also needs the right context, and that becomes the focus of the next chapter. Prompt engineering has also drawn a lot of criticism, with some people dismissing it as not a real discipline. But the fact that it is easy to start does not mean it is easy to do well, and that misunderstanding fuels a lot of the debate. A practical reminder is that robustness can sometimes be de-emphasized in benchmarks, even though it matters in real use. If a model is brittle, small prompt changes can expose weaknesses that benchmarks may hide. Most of the time, using the wrong chat template hurts performance. Rarely, the mismatch can accidentally help, but the safe assumption is that following the expected format matters. This is a very practical issue, not just a theoretical one. In real projects, people often spend time debugging because the template changed between model versions and the tooling didn't keep up. To reduce that friction, many APIs handle the special template tokens for you. That design choice helps users avoid subtle formatting mistakes. Context windows are expanding quickly, and that changes what models can handle at once. When these numbers are reported, it's important to know whether they are public and actually available for use. Needle in a haystack tests are not just abstract benchmarks. They can be adapted to real situations, like checking whether a model can retrieve an important detail from a large body of text. Remember that a language model does not inherently know which text was written by the user and which text it generated itself. That is why prompt structure and delimiters matter so much. Some prompt engineering ideas come from public guides and examples, including ways to split work into parallel pieces. Those patterns are useful because they show how prompting can be structured, not just written as a single block of text. A model may also get better at writing prompts if its training data includes many examples of prompts from the web. In other words, prompt writing skill can be learned from exposure to prompt-like text. This section also reinforces a simple philosophy. When something is unclear, ask to see the prompt itself. That makes debugging and evaluation much easier than guessing from the output alone. Prompting is not just about quality. It can also affect safety and reputation. Bad outputs can spread misinformation or create brand risk, so evaluation has to look beyond correctness. In some cases, prompt-related behavior has even led to serious security issues in real tools. That's a reminder that AI systems must be treated like software systems, with the same attention to vulnerabilities. There are many public collections of prompts, but their value can fade as models change. A prompt that works well today may not stay relevant for the next model release. Another open question is whether prompts can be treated as intellectual property in the same way as written works. The legal and commercial rules here are still unsettled. It's also worth noting that modern models are surprisingly tolerant of typos. That resilience is useful, but it should not make us assume they understand every messy input perfectly. A few prompt examples are just playful or unusual. Those cases are included to show the breadth of model behavior, not because the wording itself is especially important. You can't talk about prompt or input sanitization without remembering the classic injection joke. It captures a serious point. User input can become dangerous when a system treats it as trusted content. Repeating text in a prompt may seem harmless, but it can be used in repeated token attacks. The key idea is that even simple-looking inputs can be engineered to stress a model in unexpected ways. Some extraction attacks do not begin with carefully crafted prompts at all. Instead, they sample from real text corpora and search for outputs that reproduce training data verbatim. One reason these behaviors improve is that larger models generally learn patterns more effectively from data. That doesn't solve every problem, but helps explain why scale changes capability. The final takeaway is caution. Security and reliability still limit adoption in sensitive settings. Until those problems are addressed, many high-stakes domains will move slowly.